So good morning to lecturer and my fellow friends. Today I want to talk about how to teach the question A of our assignment. So the question of A is Mamayat Bakery produced red velvet, chocolate and pandan cake. The process require two types of skilled labor, baking and packaging. So the following table give the availability of the resource, the uses by the three product and the selling price per unit. So we can see here the resource is egg, baking, packaging. So the requirement resource per unit is a red velvet, chocolate and pendant. So the weekly availability. So we can see Mamayat Bakery can the can produce maximal 20 units of egg per week. Maximum 44 hours for baking per week and 8 hours for packaging per week. So our first step is to formulate an LP model to maximize the profit and find the optimum solution. So the first we must find the decision variable. So clearly here we can see the first x1 is the number unit of red velvet cake. So x2 is the number unit of chocolate cake. So x3 is the number unit of pendant cake. Okay, and the next step is we find the adjective functions. So clearly here our adjective function is the selling price. So z is equal to 16x1 plus 30x2 plus 20x3, which refer to the number of red velvet cake, chocolate cake and pandan cake. So the third step is we find the constraint. So our first constraint is for x1 plus 2x2 plus 1.5x3 smaller than 20. So the second constraint is x1 plus 6x2 plus x3 smaller than 48 hours. So the third constraint is 2x1 plus 1.5x2 plus 0.5x3 smaller than the formulation, which is to maximize z is equal to 60 x1 plus 30x2 plus 20x3. Then we redo it in standard form. So z minus 16 x1 minus 30x2 minus 20x3 equal to 0. So this is our standard form. So for the constraint is 4x1 plus 2x2 plus 1.5 x3 plus s1 equal to 20. So 8x1 plus 6x2 plus 3 x3 plus s2 equal to 48. And the third constraint is to x1 plus 1.x2 plus 0.5 x3 plus s3 equal to 8. So we add s1, s2, and s3 as a decision variable for all these constraints. So x1, s2, x3, s1, s2, s3 must greater than 0. So that's all for me. About teaching our first step of question A. So the next step, I give all this duty to Nova. Thank you.
So this is our initial table. So our basic variables are s1, s2, s3, and non-basic variables are x1, x2, s3. So this is our table. Our BV is basic variables are z, s1, s2, s3. Our row 0, 1, 2, 3. Then z, our row is z, x1, x2, x3, s1, s2, s3, RHS ratio. So these are our table U. Hope you all can see that. So x1 is the entering variable EV as it has the most negative coefficient in row 0. S3 is the leaving variable LV as it has the smallest ratio. So from based on table U1, still the basic variable will be S1, S2, X1, and non-basic variable will be X2, X3, and S3. So the elimination will become R row 0 will be eliminated like row 0 plus 60 R3. R1 will be R1 minus 4 R3. R2 will be R2 minus 8 R3, and R3 will be R3 over 2. So after that, this is another table 1. So it will be like this. Then x3 still is the entering variable as it has the most negative coefficient in row 0. So s1 is the leaving variable LV as it has the smallest ratio. So our table U2 will be like RO will become RO plus 5 R1. R1 will become 2 R1. R2 will become R2 plus R1. R3 we have to R3 minus R1 over 4. So this is our table U2. You can see from our we have our diagram. So x1 equals to 2, x2 equals to 0, x3 equals to 8, s1 equals to 0, s2 equals to 24, s3 equals to 0, z is equals to 280. So the total profit is 60 in bracket 2 plus 30 in bracket 0 plus 20 in bracket 8 will be equals to rm 280. So Mama Yet Bakery needs to produce 2 units of red velvet cakes and 8 units of pandan cakes to maximize their revenue to 200 RM 280. That's it.
So now we proceed to question B. For this question, we want to find out if the current basis will remain optimal if a unit of pandan cake has been increased to 22 ringgit here. Okay, from initial 20 ringgit. In this model, we let D1, basically D1, D2 and D3 represent the change in the unit revenues for red velvet, chocolate and pandan cakes respectively. So this one, okay. So this is our original objective function, which is z is equals to 60x1 plus 30x2 plus 20x3. Okay. From this, we incorporate the change in the unit of revenues in the objective function and will become maximum. This one. Okay, so we need to consider where all objective functions change simultaneously. So we do the modified optimal table below. So this is the one. Okay, and the entries in the top row are the change of D associated with variable X. Therefore, if you look at this, D1 is for X1, D2 is for X2, and D3 is for X3. Okay, and for the slack variable is equals to 0. So S1, S2, and S3 is equals to 0, like that. Okay, for this left column, our basic variable is X3, S2, and X1. As to that, our Z row element is 1. Okay, our S2 element is 0. Okay, and the X3 is D3, and last one, element X1 is D1 here. Okay, from here we can find our reduced cost for NBV. So what is our NBV? Our NBV is this one, X2, S1, and S3. And we multiply its column element with the element at leftmost column. We add them up, then we subtract the top row element. So basically it's like this now. I'm going to show you. This is the calculation for all the NBVs. Okay, so after you calculate all of these, okay, your answer we get on the right side. Okay, this is the answer. Okay, so we apply the same like all of these we can calculate to get the NBVs, reduced cost for each NBVs. Okay, so do take note that the reduced cost for BV is always 0, always 0. So I'm gonna go down here. So the simultaneous optimality condition that correspond to our NBV are this one. Okay, as the price of pandan cake has increased to 22 ringgit, the new objective is Z. Hold up. Z is equals to 60x1 plus 30x2 plus 22x3. And that is the new one. Okay, so from here, we do the simultaneous changes between the old objective function and new function. Coefficient in the new function minus coefficient in the old function. Okay, thus, ta-da, this one. Okay, then we substitute the changes into the above optimality condition. It is satisfied if all of our reduced costs are non-negative, other word positive numbers. So this is the one. Okay, for X2 is more than 0, thus it is satisfied. S1 is 14, it is also satisfied. S3 is 2, so it is also satisfied. As all of our reduced costs are satisfied, this shows that the proposed changes will keep the current solution optimal with a new maximum revenue that can be calculated using the new objective function. Okay, so we substitute X1, X3 from question A into the new objective function. Ta-da. Okay, hence the maximum revenue for this change is RM296 ringgit. Thank you.
So, for question C, the question asks that we have to determine the dwell price of the baking hour and its allowable range. If available baking hour is decreased by 21 hours, will it change the optimal production quantities? So by this part, we have to actually decide on what happened if the right hand side of a constraint is changed. So we need to actually do all of the modification before that. So by looking at the LP, we have to add the variables of D1, D2, and D3 to each of the constraints. So we can call the first constraint as operation A, and then we have to add D1 into the right hand side of the equation. For the second constraint, we call it as operation B, and we add D2 into the right hand side of the equation. And operation C is the third constraint, and we add D3 into the constraint, in the right hand side of the constraint that is. So that means that there's 3 variables for the 3 constraints. So after we modify the LP, we also have to modify the optimal tableau. So we can also do this from the start, from the initial tableau, but even after we're doing it, it's still going to be the same, which is that the optimal tableau, we have to add 3 new columns to the right side of the right hand side, which is the D1, D2, and D3 of the optimal tableau. So from that, we actually have to we can copy the value of S1 and S2 and S3, all the columns, value in the column. We can just directly copy into D1, D2, D3, because if we do it for the initial table, we find out that the value for S1, S2, S3 is the same for the value of D1, D2, and D3. So we have to find the optimal solution for each of the BVs, which is Z, X3, S2, and X1 and S1. So for Z, we just take it from the right hand side to D3. So that means that 280 plus 10D1 plus 0D2 and plus 10D3. Same for X3, which is 8 plus 2D1 plus 0D2 minus 4D3, since this is a negative number. And for S2, we have 24 plus 2D1 plus D2 minus 8D3. And for the final constraint, we have for final BV, we have x1, which is 2 minus 0.5 d1 plus 0 d2 and plus 1.5 d3. So then we can list out the optimal solution, and this is the finished result. And from this, we can find the new objective function, which is 200 z equals to 280 plus 10d1 plus 0d2 and plus 10d3. So from this, we find that a unit change in operation A capacity of D1 either plus minus 1 unit changes Z by 10 ringgit, and also operation B capacity changes Z by 0 ringgit, and also for operation C, the capacity of either 1 plus 1 plus minus 1 hour changes Z by 10 ringgit. So the dual prices, we can find the dual prices are, for operation A is 10 ringgit, for operation B is 0 ringgit, and for operation C is 10 ringgit. So that means that for any value change to the right hand side of operation A and C, we change it by 10 ringgit. Change Z, the objective function, by 10 ringgit, while B will change it by 10 ringgit, by 0 ringgit. That means that there would not be any change if operation B has any change in the right hand side. So now we have the feasible ranges, in which that 8 for x3 we have 8 plus 2d1 minus 4d3, s2 we have 24 plus 2d1 plus d2 minus 8d3, next one we have 2 minus 0.5d1 plus 1.5d3, and all of them has to be bigger than 0, or at least a non-negative number, because the right hand side could not be negative. So the question earlier asked if available baking hour is decreased by 21 hours. So, since we know that the baking hour is operation B, which means that it is the second constraint, and that means that the variable for it is D2. So that means we have to substitute the value into D2, which is 21. And since D1 and D3 have no changes, that means the value for it is 0, since there's no change to it. So we substitute the three values into the feasibility conditions that we have, the range it is. So that the x3 is equal to 8 plus 2 times 0 minus 4 times 0, which is equal to 8. And 8 is bigger than 0. So that means that the condition for constraint 1, for solution for operation A, that is feasible. And for operation B, S2 is equal to 24 plus 2 times 0 plus 21 minus 8 times 0, which is equal to 45. And 45 is bigger than 0, which means that operation B is feasible. And x1 for operation C is 2 minus 0.5 times 0 plus 1.5 times 0 is equal to 2, which is also bigger than 0. That means that operation C is also feasible. Thus, the current basis remains feasible with new solution values. That means that we have to substitute the new value for our equation into the new z objective function. So that means that z is equal to 60 times 20 plus 30 times 0 plus 20 times 8. So that means that the value, the maximum revenue is 280 ringgit, which is still the same as the initial optimal solution as in A. That means that it's true to the dual price, which is 0 ringgit. That means that any change to operation B does not change the Z value. So that's it for me. Thank you very much.
So I will continue for the last question, which is question D. Would you recommend Mamayat Bakery to buy eggs at price RM15 ringgit per dozen? So if the price of 1 dozen egg is 15 ringgit, so 1 unit of egg is estimated to be RM 1 ringgit and 25 25 cents each. As per week, Mamayat Bakery is using 20 units of eggs. The costing estimated for 20 eggs would be RM25 ringgit if they buy the 15 ringgit per dozen. Whereas if they buy 2 dozen, the cost would be 30 ringgit. As the revenue gain for the week is RM280, Mamayat Bakery will still obtain profit if they choose to buy the eggs. Thus, we would recommend them to buy the eggs at a price RM50 ringgit per dozen.